Hello everyone, welcome to the first video for the section 2.7 notes. Here we're going to be basically finishing up our general discussion about stuff having to do with functions, having to do with graphs of functions, stuff like that. And here what we're interested in are a couple of characteristics about functions that we did not talk about before, which are things like symmetry. And then also we want to talk about basically this idea of piecewise functions. And then we will talk about a couple of things like minimum, maximum, that kind of stuff. But let's just get into it with this idea about the symmetry. And so the first kind of symmetry that we'll talk about, which this one will be important for the idea of functions. Here we're not talking about functions necessarily, just when we're talking about symmetry. We're talking about graphs, and we understand from our discussion of graphs previously that it's not necessary for a graph of something to actually be a function, because we had that thing about the vertical line test rather, where say for example you just have a graph that is maybe a circle or something. It's possible to have a graph like this, but by doing the vertical line test you'd see if you draw a line through this one, the line crosses twice, and so this thing actually is not a function. However, circles, of course, are very symmetrical things, and so this circle, where I have placed it actually, is not going to allow it to be symmetric in the ways that we're talking about. But imagine if a circle is just along here like this, where, you know, this y-axis over here is just a perfect diameter of the circle. Then the circle is actually symmetric across the y-axis. It would be possible to place a circle over here, and it should be a little bit higher, because what I'm trying to illustrate is that a circle like this, imagine if this is a perfect circle, where this x-axis here is the diameter of the circle, then this one would be symmetric across the x-axis over here, and then it would be possible as well to draw one that would be symmetric about the origin. Now, for me to draw a circle that's symmetric about the origin, which actually I'll put one here on this graph, this one should just have its center on the origin. In this case, it's symmetric about the origin because if you pick a point over here that's on the circle, and I'll do this one in red just so it's more clear. If you pick a point on the circle over here, for it to be symmetric about the origin, we should have that if you come just exactly to the opposite side of the origin from that point should be on the graph as well. And we can see that actually for the circle that's symmetric about the origin, it is symmetric about all three things. It's symmetric about the y-axis, because if you pick any kind of a point and you just reflect across the y-axis, that point is there. You can reflect across the origin, or else if we pick a point here and you reflect across the x-axis, that point is also there. So this circle is super duper symmetric, but without getting off too much into circles, we're really here to just talk about symmetry for any kind of equation at all. And the equation being symmetric, of course, what I'm referring to is whether the graph of that equation is symmetric. So we have a couple of ways that we can test that. If we're checking whether or not the graph of an equation is symmetric with respect to the y-axis, what we would check is what happens when you put in negative x for x. Because when we're talking about the y-axis, you know, on the right side of the y-axis over here, x is positive over here, and maybe we could even be pointing at a specific x, like maybe this value. And then if we come over here on the other side, and this one is negative x, if a graph is symmetric about the y-axis, we would expect the graph to have the same y value for x and for negative x whenever x is on the graph. And so we could actually check that one for number one. We're going to see what happens whenever we plug in, we'll say y equals negative x cubed. Well, you know that if you cube a negative number, because this one's like negative x times negative x and then times negative x again, when we do two of them, it becomes x squared, but then when we go times negative x again, it's going to be negative x cubed. And so this one we don't get the same thing. We're supposed to get the same y value whenever we plug in negative x for it to be symmetric with respect to the y-axis. So for number 1, it is not symmetric with respect to the y-axis, but we can tell that it will be symmetric with respect to something else. First, let's check the one for x-axis. To tell if it's symmetric with respect to the x-axis, you plug in negative y, because if you come over here and something is symmetric with respect to the x-axis, like maybe onto, we had one over here, this circle that I'm thinking of. This circle over here, we said that this one was symmetric with respect to the x-axis, and you can check that for just a given x value, like maybe for this x value over here, it has the positive y value, and then it has also the negative of the same y value. This one will go, this value over here should be like xy, and then this should be the point like x negative y, whatever this x value is. We'll say x, and actually I will call it x0 just to differentiate all of these other x's that are on the same graph. And so those 2 points will be on the same one. And so we could check what happens whenever you plug in negative y. It goes negative y equals x cubed. This one is not the same equation, because here y is positive, here y is negative. They're different, so it's not symmetric with respect to the x-axis. And we could even simplify this one a little bit. It's not really simplified, but it just seems more natural to have the negative on the other side, because we like it to just say y equals blah blah blah. Now the last one that we're going to check, what about symmetric with respect to the origin? That's the one where we want to check the fact that, and here this is what I was trying to explain earlier, is that this point over here, let's call this the point xy. If that is a solution of the equation, that means that that point will be on the graph of the equation. We should have another point on the graph, though. We said this point over here should also be on the graph, which is negative x negative y. And for a point to be on the graph, that means it has to be a solution. So in other words, we're trying to check, is negative x negative y also a solution to the equation? And the way we could tell that it would be a solution is that it should be, basically if we simplify it, we put that in there and simplify it, it should give us the same equation. And so that's what I'm going to do here. I'm carrying on with this one, checking what happens if we put in negative y for y, so it will go, there it will go negative y, equals, and then we're plugging in for x, negative x. And so we'll go negative y on this side. We already figured out this one should go negative x cubed. And then we could also just multiply both sides here by negative 1. And it will go y equals x cubed. And it is the same. And so it's actually symmetric with respect to the origin. This one, number 1. And what we're kind of building up to here, this whole point of this talking about symmetries, we want to talk about functions, not graphs of equations, because this class mostly we're interested in functions. And a couple, let's see, for example, number 3. This is the graph of a circle, and so it's not even a function at all, but we could still discuss the symmetry of that one. But here, really what we would like to talk about is the symmetry of these functions. And here we don't use the word symmetry anymore. We talk about whether a function either is even function, or else odd function. Even function here is the same thing. Even and symmetric with respect to y-axis is the same. Odd function, that's the meaning of symmetric with respect to the origin. And you can remember it probably because origin and odd both start with O's. That's how I remember it. Odd function is symmetric with respect to the origin, and imagine what kind of name should we give for a function if it's symmetric. A blank function is symmetric with respect to the x-axis. Could something go here? Could we call it a function? Of course, if you were paying attention, this cannot actually be a function at all. It's no function. If something is symmetric with respect to x-axis, it's not a function at all. So we don't bother with that one. We only have these two definitions, even and odd. And the way that we will check this one, we want to start out the same way. You notice that what you're checking for is what does it look like f of negative x. We say if we plug in negative x and we actually end up getting the same thing, the same y value for x and negative x, that means it's symmetric with respect to y-axis. If the negative of x value gives us actually just the exact negative of the corresponding y value that goes for f of x, then it will be symmetric with respect to origin. So either way, we want to start out by plugging in negative x. Find out what is negative x. Is it just the same thing as f of x, or is it exactly the negative of f of x? And so what we would look for here, we plug in negative x into these, and then it will go minus, I'm just doing number 5 here, trying to plug in into these x's the value negative x, and so it should go negative x squared and then go plus 2. If you raise something to even power, like here to the 4th power to the 2nd power, it will be always a positive number, so this one should go x to the 4th power minus, and then this one negative x squared, it just becomes x squared, and then goes plus 2, and so it is x to the 4th minus x squared and then plus 2. And you notice that's the same thing as f of x. So f of negative x is the same thing as f of x. That means that this one is even function. And something to notice about this one, it works for polynomials. Do you notice what the powers are for these terms? 4, 2, and then this one's basically like x to the 0 power. 0, what kind of number is that? Is it even or odd? Of course, 0 is an even number. And here you notice that all 3 of these powers are even. And if you have a polynomial that has all even powers for the x terms, it will be an even function. If you have polynomial with all odd powers for x, it will be odd. And if you have some type of a mixture, like what about this one? This one goes x cubed minus x. Since there's no power there, it should just go to the 1st power, and then plus 3, but since it's a constant, we understand we could put here like x to the 0 power, because x to the 0 power, anything to the 0 power is just 1. So it doesn't matter if we multiply there. Do you notice these powers 3, 1, and 0? It's a mix, because these ones are odd powers, and this one is even power. So you can check for this problem. We know it will be neither, because it does not have all odd powers to be odd, it does not have all even powers to be even. It has a mix, so it will be neither, but you could check that one. But anyways, I would just write here for that one. Neither, because I'm using this shortcut, sorry for the handwriting there, about using the powers for the polynomials. Of course, that only works whenever you're talking about polynomials. If we were doing something else, then it will not work. Only for polynomials. But all 3 of these problems are polynomials, so it would work for us. Here this one has both odd powers because this goes x to the 1st power, so this one for sure will be odd. But you can check by checking what is f of negative x. You will see that it is the exact negative of what we have here for f of x. But anyways, we will take a look at some of the other last little bits about functions in the next video. And thank you guys for watching.